Bismillahirrahmanirrahim. Law of mass action. Law of mass action, according to the statement, says rate of reaction is proportional to the product of molar concentration of reacting substance raised to the power coefficient as in balanced chemical equation. Means greater the concentration of the reacting substance, greater will be the rate of reaction. For the derivation of Kc expression, we consider a general reversible reaction in which capital A, B, C, and D are chemical species which are involved in that chemical reaction, and small a, small b, small c, and small d are the coefficients that are used to balance a chemical reaction. And we normally represent these reacting or substance or products with a scare bracket. Their scare bracket normally represents the active masses described in mole per dm cube, that is in fact represent their concentration. According to the law of mass action, we said rate of reaction is directly proportional to the product of concentration of reacting substance. In case of the forward reaction, capital A and capital B will be considered as the reacting substance. We will write their concentrations. Reacting substance A or B we are represented, and we have to represent their concentration in terms of molarity, mole per dm cube, so we will represent it with the scare bracket. Similarly with the B, and their raised to power coefficients as in their balanced chemical equation. Power coefficients we represent small a and small b. Similarly, for reversible reaction, C and D will be considered as the reacting substance. The rate of reverse reaction will be proportional to concentration of reacting substance C and D, and small c and small d will be represented for their coefficients in the balance equation. If we remove proportionality, we can place constant for the forward reaction. Kf represents constant for the forward reaction, equation 1. Similarly, for removal of proportionality, we have placed Kr. Kr is constant of the reverse reaction. At equilibrium, rate of forward reaction will be equal to rate of reverse reaction. For expression of from equation 1, we have placed Kf is equal to Kf and product of A and B. Similarly, from equation 2, we have placed expression for rate of the reverse reaction. Then we have placed both constants on the same side, Kf and Kr, and then variables on the other side. Then we replace these both constant Kf and Kr with another constant Kc, that is called as equilibrium constant, and that is the final derived expression. It's a final derived general expression of Kc.